First, my apologies for having to give this talk remotely. I haven't been feeling so well for the past 3 days.
Bernhard, wait a second.
This talk, well, maybe first a few memories. I first met Michel in the late 1980s in Peter Gabriel's seminar in Zurich. Michel gave a talk, if I remember correctly, it was about representations of maximal orders. Now, as you perhaps know, Peter Gabriel was often very critical of the talks given in that seminar, but in Michel's case, he was really enthusiastic about the talk. So it was a happy beginning of a long sequence of nice mathematical adventures with Michel. Now, in this talk, my aim is to present an application of Michel's superpotential theorem to Amiot's conjecture from 2010. And application of Michel's superpotential theorem to Amiot's conjecture from 2010. Now, Michel's superpotential theorem is a structure theorem for 3 Calabi-Yau algebras, and Amiot's conjecture is a structure conjecture for certain 2 Calabi-Yau categories. And the problem in the proof is the fact that 2 is different from 3. If 2 was equal to 3, Amiot's conjecture would be an immediate consequence of Michel's superpotential theorem. Now, the plan is as follows. First, I would like to present a series of examples where Amiot's conjecture holds, and these examples are constructed using preprojective algebras. So I will make some reminders on preprojective algebras. There will be some overlap with Junyang Liu's talk. Then in a second part, I'd like to recall Michel's superpotential theorem. And in the third part, I would like to give the promised application. It will be a proof of a slightly modified, I'm tempted to say improved, version of Amiot's conjecture. Okay, so let me start with the preprojective algebras. Okay, I will only work with preprojective algebras associated with ADE Dynkin diagrams. So let's take delta and ADE Dynkin diagram. And let's take Q, an orientation, a quiver, which is an orientation of this diagram. For example, you can think of the quiver Q, which is the linear orientation of the A3 Dynkin diagram with arrows A and B. And then we need a ground field, and the ground field could be any algebraically closed field of characteristic 0. Let's take the complex numbers for simplicity. And then let me write pi of q for the pre-projective algebra. Of this quiver Q, yes, introduced a long time ago by Gelfand and Panamarioff. In 1976. And well, over the ground field, of course. And so in our example, pi of q is given as follows. Yes, we take the given quiver, we add a new arrow in the opposite direction for each given arrow, and we add a relation which can be written in a compact way as the commutator of the old arrows with the new arrows. Gamma runs over all arrows of q. This is the compact way of writing it, but we can also write it one relation for each vertex, then it becomes 3 relations. So here it would be minus b star b equal to 0, bb star minus a star a equal to 0, and a star equal to 0. Now, a few remarks on this algebra. First of all, it is a finite dimensional algebra. It contains the path algebra, and if we restrict it to a representation of the path algebra, we get the sum of all indecomposable representations, of which there are only finitely many, because we have started from a Dynkin diagram. And it is finite dimensional, and it is self-injective, which means that it's injective as a module, as a right module over itself. Okay, and then yes, if we look at the category of finite dimensional modules, finite dimensional, right, IQ modules, then this category becomes a Frobenius category. So it is an exact category in the sense of Pullen. Well, here it is even abelian with enough projectives and enough injectives, and where these two classes coincide. And so if we form the stable category, mod by Q underlined, yes, this is the associated stable category. So it has the same objects as the module category. And morphisms are given by quotients. Stable between L and M is the quotient of all pi q linear morphisms modulo those which factor through a projective injective object. Okay, and this then becomes a triangulated category. Yes, this holds for any Frobenius category by an old theorem due to Dieter Happel. Every short exact sequence of modules gives rise to a triangle in this category, and the syzygy functor gives rise to the inverse shift functor, the inverse suspension functor in the category. Then a more subtle property is the two Calabi-Yau property, namely, as shown by Bill Crowley-Boovey in 2000, is two Calabi-Yau as a triangulated category, which means that we have cell duality in dimension 2, x1 between L and M, the dual of x1 between L and M, D is the K-dual, identifies in a bifactorial way with x1 from M to M. Okay, now from the point of view of classification of indecomposables, these pre-projective algebras are hopeless as they are wild, except in 6 cases. So we cannot hope to classify indecomposables. In 6 small cases, if delta is A1, A2, A3, A4, D4, or A5. And so from this point of view, it's, well, an extremely difficult situation. However, PyQ, or its stable module category, has another more recent important finiteness property, namely it is 2 representation format in the sense of gamma. In 2007, yes, this is another finiteness property, and it means that the module category, or equivalently the stable module category, contains what is called a 2-cluster tilting object. Okay. And this 2-cluster tilting object, it even contains a canonical such 2-cluster tilting object. Let's denote it by T canonical. It was constructed by Geiss, Leclerc, Schröer in 2007. And the philosophy of Amiot's conjecture is to describe this 2 Calabi-Yau category, if possible, in terms of the endomorphism algebra of any 2-cluster tilting object. Okay, but before making that more precise, let me give you the definition of the cluster tilting object. T in stable model category is 2 cluster tilting. If it has 2 properties, first of all, it is too rigid, it has no self-extensions in degrees strictly between 0 and 2. Well, here there's only one such degree. And secondly, it is a 2-step generator. Which means that for each object M, there is a triangle T1, T0, M sigma T1, where the Ti's belong to the closure of T, the object T, under finite direct sums and direct sums. Okay. Yes, so we have this nice object which allows us to present every object in such a way. And so it is natural to try and describe the whole category in terms of the endomorphism algebra of this object. Let me give you an example. A small example that QB, the original quiver, is just the A4 quiver. Okay, and then, well, I will not give you the object itself explicitly, but just its endomorphism algebra, its stable endomorphism algebra is given by the following quiver with relations. A, B, C with relations A, B equal to 0, B, C equal to 0, and C, A equal to 0. Okay. Now, perhaps you recognize that this can be interpreted as the Jacobian algebra of a quiver with potential. And T is the Jacobian algebra let's write it JRW of, well, the quiver R A, B, C, and the potential is just A, B, C. Yes, whenever we have a quiver with potential, yes, then we get the Jacobian algebra by taking the path algebra of our quiver and imposing the relations obtained as the cyclic derivatives of the potential. Yes, if I take the cyclic derivative with respect to A, I have the C. Cyclic derivative with respect to B gives me CA, and the cyclic derivative with respect to C gives me B. Okay. And well, we would like to describe our category in terms of the endomorphism algebra, but that is usually not possible. However, as discovered by Ginzburg in 2006, the Jacobian algebra has a differential graded refinement, now called the Ginzburg algebra. Differential graded refinement. the Ginzburg-Digi algebra. Okay, let me give you the instruction in this example. Yes. So what is it in this example? Yes, it's denoted by gamma W. So gamma W is the completed weighted half algebra of a quiver R tilde, which looks as follows. So as we take 1, 2, 3, well, we keep the given quiver with arrows A, B, C, and then we add new arrows as in the construction of the pre-projective algebra, but these new arrows are now in degree -1. And now we also add loops. One loop for each vertex. And the loops are in degree -2. And we endow this completed graded path algebra with a differential. The differential of the loops is again a commutator. So for example, the differential of T1 is going to be CC star minus B star B. And then, okay, notice that the degree decreases by 1 as it should. And then if we take, for example, the differential of a star, that is defined to be the cyclic derivative of the potential with respect to A. Okay, and so you see, well, we get a nice differential graded algebra, which is connective. Which means that its homology in strictly positive degrees vanishes. Which P W vanishes for all P greater 0. And if we take homology in degree 0, then we find the Jacobian algebra clearly. Okay. And so, well, it is this Ginzburg algebra is a refinement in the sense that in degree 0, we recover the Jacobian algebra, and then in negative degrees, we get higher homological or homotopical information. And this information is what we need if we really want to reconstruct the our two Calabi-Yau category. So this is the first example of, this is an instance of Amiot's conjecture. Here it is Amiot's theorem. She proved this in 2009. Namely, we have a canonical triangle equivalence between the cluster category associated with the quiver potential and the stable module category. And I should define the cluster category. Okay, this is defined as the quotient of the perfect derived category of the Ginzburg algebra by the perfectly valued derived category of the Ginzburg algebra. Yes, so this category, the perfect derived category, is just the, well, if you like, the subcategory of compact objects inside the unbounded derived category of gamma. And this is the perfectly valued derived category. Yes, this is formed by the DG modules M, whose value is perfect, and by definition, the value is just the restriction to the ground field. So this should be perfect. Of course, you could also say that it has homology of finite total dimension. This way of saying it has the advantage that it generalizes to an arbitrary ground ring instead of field K. Okay, and maybe one more word. Yes, of course, the free DG module of rank 1 belongs to this perfect derived category. And so we have its image in the cluster category. And as expected, the equivalence maps the free module of rank 1 to the given canonical cluster tilting object. Okay. Yes, and Matthew Preston has made a remark. It is really for A4. We can discuss this later. Okay. Yes, so in this instance, we have obtained a description of a two Calabi-Yau category with cluster tilting object as a cluster category. And the idea is that every two Calabi-Yau category with a cluster tilting object should be given in this way. Well, everyone satisfying suitable technical assumptions in addition. Okay, so that's the conjecture. Okay, so let's take C, a home finite. Peruvian. Yes, it turns out that this quotient is actually Peruvian. Triangulated category. Such that the following hold. So first of all, C should be what is sometimes called algebraic. And one way of saying this is that it is triangle equivalent to the H0 of some pre-triangulated DG category. Okay, then second hypothesis, C is two Calabi-Yau as a triangulated category. And then third condition, C contains a two cluster tilting object T. Okay, so these are the assumptions, and then there should exist a quiver with potential, as in the example, RW, and an equivalence between the cluster category associated with the corresponding Ginzburg algebra and the given two Calabi-Yau triangulated category, which maps the free model of rank 1 to the given cluster tilting object. And this implies in particular that the endomorphism algebra of the cluster tilting object is the Jacobian algebra. yes, it is not hard to check that the endomorphism algebra of this free module in this quotient category is precisely the Jacobian algebra, and so the Jacobian algebra should also be the endomorphism algebra. So this endomorphism algebra is described by a quiver with potential. Now, over the years, quite a bit of evidence has been accumulated for the conjecture. The first piece of evidence actually predates the conjecture. It is okay if the endomorphism algebra of the cluster tilting object is a hereditary algebra. If it's a global dimension 1, then the quiver R will be acyclic, and one can check that we have the expected equivalence. Then, of course, it is okay in the motivating example. And at least for the canonical cluster tilting object. Then, well, there are quite a lot of other examples. Let me classes of examples. For example, it holds if C is the G equivariant category of coordinatory modules, where R is a power series algebra in 3 variables, and G is suitable cyclic group acting on it. Yes, this is on the one hand due to Amiot and Reiten, and independently to Michel and his student Louis Tanhauer de Volksy. Published a bit later. And yes, and there are many other classes of examples. Now, what about the general case? Yeah, let's look at the conjecture once more. Let's try to criticize the conjecture. Well, in the first condition, we have this assumption about the existence of an enhancement. Yes, so here we postulate the existence of this higher structure, but then in the second condition, we don't use this higher structure. The 2 Calabi-Yau condition is just for the triangulated category. Yes, so this is a bit incoherent. What we should do, well, from this point of view, is that we should take a 2 Calabi-Yau structure not on the triangulated category, but on this DJ category itself. Okay, so this is, let's say, an incoherence in the conjecture. Yes, the 2 Calabi-Yau structure in the second condition should not be for the triangulated category on the given category C, which is just the H0 of A, but on A. Yes, just from an aesthetic perspective, that's what the conjecture should be like. Okay, and now the theorem is that if we take this modification, then it is actually true. And so this is joint work with Junyang Liu, who is present. This in this modified form the conjecture holds. And the main tool for proving it is Michel's superpotential theorem. So let me recall Michel's theorem. Okay, this is a theorem which appeared in 2015. We take A, the smooth connective complete DG algebra endowed with a left 3 Calabi-Yau structure. Then A is quasi-isomorphic to a Ginzburg algebra for some quiver with potential. And I should emphasize that Michel proves his theorem in arbitrary dimension greater or equal to 3. And here I will only use it for, and quote it and use it for dimension 3. And yes, of course, an important point is that the converse also holds. The Ginzburg algebras have these properties. In particular, they have these left 3 Calabi-Yau structures. And this is also a theorem by Michel from 2011. And maybe I should remind you of the terminology. So now smooth means that the algebra viewed as a bimodal over itself is perfect. Then complete means that we actually have a DG algebra in the category of pseudo-compact vector spaces. And the DG algebra has to satisfy a certain technical property, which I will not make explicit, but which also holds, of course, for the Ginzburg algebras. Then the left 3 Calabi-Yau structure. This we have already seen in Damien's talk. So it's a class. Let's call it beta in negative cyclic homology of A, which is non-degenerate. Which means that its image under the following isomorphism, well, sorry, the following morphism, yes, we go from negative cyclic homology to negative Hochschild homology, and this is isomorphic to form in the derived category of bimodals from A to sigma minus 3 of A, and this should be an isomorphism. Okay, so this is an important property. the key property, of course. And now, yes, oh, sorry. The dual bimodule dual SHH is the bimodule. Okay, and now let me show you how we can apply this to get the conjecture. Okay, so we take C from finite algebraic. So we say that C is the H0 of its DG version, CDG. It has a cluster tilting object to a cluster tilting object T. And now here what we need is a right to Calabi-Yau structure. Okay, what is that? It's a class alpha in the K-dual of cyclic homology in degree -2, which is non-degenerate in a slightly different sense.
Bernhard, was it defined HN3A? Did you define it?
Hn is negative cyclic homology, which is often also denoted by HC -3. Yes. Yes, and so here we have a class in the dual of cyclic homology in degree -2, and it should be non-degenerate in a slightly different meaning. Again, its image under the following map is an isomorphism. Yes, we can go from DHC -2 C DG to the dual of Hochschild homology in degree -2 of CDG. And this is isomorphic to morphisms in the derived category from the identity bimodule to sigma -2 of the K-dual of the identity bimodule with arguments reversed. Yes. An isomorphism. And so these are the data and what we would like to construct. Is an exact sequence, well, is a quiver with potential RW and an exact sequence 0 PVD gamma RW perfect of gamma RW and then our category C. Such an exact sequence of triangulated categories. Okay, yes, so that's what we try to do now. Well, we know that when we have DG enhancement, then we also have a Frobenius enhancement. So we can write this also as the stable category of some Frobenius category. So E divided by the idea of morphisms factoring through projective injectives, where E is Frobenius and P in E is the subcategory of projective injectives. Now in C, we have the closure of T under direct summons and direct summons. Here we have E, and we look at the pre-image and we call it M. Okay, and now we use this to construct this type of exact sequence. Okay, well, as you perhaps know, if we have the Frobenius category, then we can obtain the stable category also as a quotient of the bounded derived category by the subcategory of bounded complexes, or homotopy category of bounded complexes with projective injective components. Okay, now this derived category is actually a Verdier quotient of the bounded homotopy category of M, and the kernel is simply given, well, by the complexes which are acyclic as complexes with coefficients, with components in E. Here we have HBP again. Okay, here we have some Verdier quotient. And here we have HB acyclic again. Okay, and now the sequence we are looking for, this sequence will be exactly this sequence. Okay, so what one then shows that is that indeed this middle quotient is the perfect derived category of some connective DG algebra gamma. Then, well, as you perhaps have noticed, this can also be viewed as the perfect derived category of the Kossel dual of gamma RW, and one shows that this is in fact the perfect derived category of the Kossel dual of this DG algebra gamma. And now, well, the thing now we would like to apply Michel's theorem to this gamma, so we need to construct the left Calabi-Yau structure, left 3 Calabi-Yau structure on gamma. Okay, and well, how can we do that? We use the long exact sequence in cyclic homology associated with a short exact sequence of DG categories. So we get in other words, we get a triangle of complexes. Yes, we start with this term. This gives us the complex computing cyclic homology of gamma. Okay, then this gives us the complex computing cyclic homology of CDG. Okay, then the next term is the shift of cyclic homology of the Kossel dual of gamma, shifted by 1 degree. And then the shift of cyclic homology of gamma. HC. Yes. Do and CHC gamma. Okay. Now gamma is connective, and so this lives in cohomological degrees less or equal to 0, and this even lives in cohomological degrees less or equal to -1. And so, so if we look at what happens here in degree, in homological degree -2, then we get an isomorphism. Yes? So we dualize HC -2 of C dg. This becomes isomorphic to the dual of HC -3 of the Kossel dual of gamma. And now cyclic homology of the Kossel dual of gamma is nothing but negative cyclic homology of its dual of negative cyclic homology of gamma. Okay, and so we can take our given class alpha here and map it to a class beta here. And then we're practically finished. There is one subtle point, namely the non-degeneracy of alpha as a right Calabi-Yau structure. We have to show that this implies the non-degeneracy of beta as a left Calabi-Yau structure. Okay, and this is a subtle point, because if we want to prove this, we have to understand this connecting morphism in a rather detailed way. But now, once we have that, then thanks to Michel's theorem, we get the required quiver with potential such that gamma is indeed the Ginsburg algebra. Okay, thank you very much, and sorry for going over time. And happy birthday to Michel, of course.